everyone. My name is Oleg Anastasyev, and I work for one of the top 10 sites of the world since 2010. Since that time, we worked hard and did a lot of progress in improvement of our infrastructure and archived with, it to the following moment. We have very reliable network. It never breaks, no packet loss. It's very fast now, so we don't even consider network delay. Wide optic channels are employed by us, so now we even not considering data size to pass from one server to another. Same net hardware is used across our data centers, and network packets reach every server in the same time. We have professional IT security team. They deployed a clever solution to fully protect our network. We have developed an automated system that makes all changes fast and unnoticeable if we need to our network. All this is managed by a single operation engineer. Her name is Elena. He's really genius. And so we have finally come to zero cost of data transport within our data centers. So where, in which point you think I lied to you just now? You're right. In every single point, all are just damn lies. And in reality, all these are called fallacies of distributed computing. They were said by Peter Deutsch and James Gosling back those days they worked for Sound Microsystem. Well, if you go to this link, you'll learn why these damn lies is in absolutely all distributed systems. Let's take a look what we truly have in OK.ru. We have 4 data centers. They are geographically in different places within Moscow. And as one can guess, there are no absolute reliability possible with remote data centers. Of course, we cannot neglect network latency because there is the speed of light and we can't overcome it. So a single round trip could cost up to a millisecond to complete. Of course, we change network topology during runtime. 400.5 distinct type of services communicating on 8,000 servers. We can't just turn all of them off, make changes to the network topology, and turn them all back on at once. So all changes are being done in runtime. And such a big network can be homogeneous. There are old hardware, new hardware, different vendors of that hardware. So maybe at least we have a single genius operation engineer. Let's take a look who are all those people working with production servers. Hardware engineers are located in data centers and generally work with iron. Network engineers manage our network, and operation engineers, not single, it's a team of 15 professionals. And developers, they work directly with production systems as well. So our model is close to DevOps here. And I personally, as a developer, so my talk today will come from this perspective. Besides these people, more than 7 million of our users use our servers. That's how they see our site. Here you can see a page with my friends list. And to render this page, we have to get the list of my friend IDs from somewhere and filter them by type. Here I've chosen to show my colleagues only. Some on them can be in my blacklist, so we must filter them out. Then we must get profile information of my friends to sort them using that information. This sorting is sophisticated. It could take various facts into account. Birthdays, is user online or not, how active this friend is to me, and so on. Then we must get stickers to show. Here you can see some nice stickers on avatars of these machos. And finally, we must calculate some numbers and summary counters to show them on page in different places. Yeah. So how could we implement this? Something like that. Yeah. That's it. That's all I wanted to tell you today. Questions? If we could find a server capable enough to store all our information in one place and can sustain all our load, we probably do this way. But we have this slightly sophisticated, so simple ways don't work at our scale. And we have 12 billion of friendships. But this does not matter much. More important that 500,000 requests come every second to query this data set. With the user profiles, it is even harder. More than 3.5 million requests come to this cluster, and this makes about 50 gigabits of traffic. It is hard to even find a single piece of hardware capable just to stream this traffic, not process, not even process. Obviously, we have no other choice but to split data across machines, so it becomes distributed system. In the distributed systems world, this works something like this. User requests come first either on web frontends or on API frontend server, if this is our native mobile application. These frontends make necessary requests to some application server. Application server works in context of business operations. Specifically, it has a business operation named retrieve all necessary information to render my friend list. And to get this data, it queries necessary microservices. Each microservice is specialized for focused purpose. There are services focused on implementing some functionality. There are also focused on storage and management of specific type of information. So to render a friend list, we have to query graph, a cluster used to store friendships, a user cache used to store user profiles, and a blacklist. Almost all of these microservices are like this. They may have, and often they do have, the local storage. This is some kind of SSD or just plain disk device to store their data. To manage data, a logic and a specialized cache may be programmed right into the instance of the microservice, sharing the single GVM. For example, for the friendships graph, a business logic could be some kind of graph traversing algorithm over its cached in memory in presentation. And finally, service has a remote interface. This remote interface is actually a business interface of a service. It stipulates what this service actually do. So in our code base, our friendship graph service interface would look like this. We can see here it has a remote method. It is called over the network using our OneNeo library. It is called getFriendsByFilter, and all what it does is obviously to get each of my friends filtered by relation type. And there is another service, user cache, which could look like this, and it retrieves user profile information by its ID. Then application server code may look like this. So we retrieve its friends here from our graph service and prepare the array list to store the results, and then looping through the friend list we just got from graph and asking is blacklist allow to show us this ID and add the profile information to the users list. All done. Let's take a more detailed look at this parameter. It has a partition annotation. This annotation means that based on values of this parameter, we will partition or shard calls to this remote service across nodes of its cluster. Every service has partitioning strategy to define mapping of parameter values to partition ID and further mapping of partition ID to exact nodes. We use various such strategies. It could be set by underlying storage technology. If microservice uses Cassandra storage, strategy is Cassandra ring, or Voldemort partition for Voldemort storage. Or if storage does not stipulate a partitioning strategy, we use this weighted quadrant strategy. All servers are divided to partitions and sets. We calculate partition from ID. There are several replicas exist within the single partition. All data are same in each of those replicas of single partition. Set of single replicas of all partitions is called well set. And we can assign a weight on it. Weight of a single set could be different for clients in different data centers. And then client selects a node by weighted round-robin algorithm. Then it sends to this selected node a request, gets a response from there, all done. So now, when we know how it works under the hood, let's look once more on this code and let's find a problem in it. Who sees the problem? You are cheating, you know the answer. Anybody? The problem is here. This code loops. And from within the loop, for every iteration, it calls a network communication many times for each of the iteration. That's where network round trip starts to play the game. Inside our infrastructure, we will spend a couple hundred microseconds just to make one round trip. And up to 1 millisecond, it has to be done if it has to be done to a remote data center. So to make 2 requests for each of my 200 friends, I have to request a blacklist and I have to request a user cache. 2 requests per friend. We will wait for 400 milliseconds. That's not much. But for someone more popular than me, 10,000 friends will take 20 seconds. And this is not clearly not acceptable at all. So what to do? How we can solve this problem? We have to show the friend list. Okay, this downs the time to wait to 10 seconds. But will you wait 10 seconds to see a list of your friends? Probably not. So the right answer is to by batching requests. Sorry. Let's refactor your remote interface to return a list of user profiles by a list of their IDs in a single call, instead of getting user profiles one by one. And then the application code would become more simple. Right after we got the friends list here, we got it filtered through a blacklist microservice, and this blacklist microservice returns only IDs who can be shown to me. And then for these IDs, I ask in one round trip user cache for user profiles data. And this kind of request, so we have only 2 round trips instead of 400 this way. And then such kind of requests will run by split and merge algorithm. It takes a list of IDs and splits them to separate lists. A list per every partition. Then, for each of these lists, it decides which node to call and merge the result to single collection. All this done on the client side. This is client-side logic. But this is how stuff works on its happy day. But we have to remember the first commandment of distributed systems. There are no reliable network. So this is the simplest possible distributed system with communicating 2 parties, one server and another. Client sends a request message, server receives it, processes, and returns back a response. Simple flow, yeah? How many failure scenarios could happen on this distributed system? Who knows? I think you are cheating again. You guys are also cheating. First row is a copied by nothing team. So, anybody? 3. Oh, good number. Actually, 7. So, what could possibly fail? Let's name them. A client can send a request and disappear from network, and the server can disappear from network as well. They can crash, or reboot, or network can fail, and or hardware can hang and fail. We can lose request or response messages. Network does not work, buffer overflows on data communicating party. A server could time out. Invalid value response could be server receives a request and responds this message client can't understand. How could this be? What happened? Sorry? No, it could be concurrence actually, but more often it's due to different versions of the client and server. Server has more recent version than the client has, so client does not really understand what server is talking to him. A protocol was changed. This is the exact way in the September Skype was down due. This is classic reason actually. And finally, my favorite, the seventh scenario, is the arbitrary or Byzantine failure. Party makes arbitrary messages, random messages at arbitrary time, without request by itself will. This could be some kind of bad intention actions, like distributed DOS attack. It could be retries gone crazy, so one of the parties starts flooding other with unnecessary retries due to bug in its logic. Amazon DB was failed in the end of the last year due to this reason. So all these 7 failure scenarios could happen on distributed system with only 2 participants. But what if they are 3? Or 4, making requests depending on the responses from each other. So you've got the idea, the number of failure scenarios goes exponentially far faster than the number of servers in your data center. So this is why most sophisticated part in distributed systems development is to consider all failure options and reactions on them. So let's talk more about failures. So what to do with the failures? The key question here is how this failure affects the state of the system, or who will notice it. If nobody and no system state is affected, this failure can be safely ignored. This is cheap and viable strategy. But if we can't ignore failures with consequences, often it is hard to tell it in advance, will there be consequences or not? Another important thing to note is that we can't fully prevent failures. They happen by their own will at the time we are not expecting them. We can only mask or hide them. As a consequence, when we build our distributed systems, we can't consider that things never break. It is meaningless. Instead, we should come from the fact that if failure possibly can occur, it will occur. The unknown here is only when it will occur. So it is important to understand how your system must react on each of these failures. We can mask failures only by bringing some redundancy to our system. This could be redundancy in information, I mean employing any kind of error correction codings. This could be redundancy in hardware, like bringing extra hardware to make replicas or any kind of hot substitution hardware architectures. And finally, redundancy in time. This could be some kind of transaction with the retries. So the time is redundant here. The last one is actually most common way for software developers to mask the failures. So let's talk about in more detail. What can be wrong with it? Let's consider this simplest distributed system. Here a client and server, and client sends a make new friendship request to the server. Server makes changes to the persistence store and boom, crashed without sending any response. Let's consider another option, same two parties. Client sends a request for operation and server crashes before making any changes to a persistent store. In the first case, client must not retry the request because state of the system is already changed. In the second case, client must retry the request because state of the system was not changed. But how client can distinguish the one option from another? What should it do? Actually, client doesn't really know. So further actions of client fall into three strategies. It cannot make any guarantees on operation success. This is most simple, still not very useful strategy, but ironically, most common in systems not built especially for to tolerate failures. You don't make any guarantees. It can never retry a request. So request is delivered at most once to a server. This one is not commonly useful, but there can be strong reasons to employ it still. And the final strategy, it can always retry a request. So request is delivered at least once or more times to a server. But when to choose which strategy? For this, let's consider make new friends operation and what processing steps could be. So first of all, we should do a transaction in ACID storage, some kind of a database tables. And for this kind of transaction, there are typically a single master, and the success of it is atomic. It is either committed or not, and we can easily roll back all changes we just made within a transaction. So and make it like it was never happened. And in the second step, we must refresh cached information in all of our caches. There are no single master, a lot of replicas, no atomic rollback is possible. Even more, there could be partial failures. Let's look at the first step first, and let's introduce the concept of idempotency here. So idempotence is the property of operation. So this operation can be applied multiple times without changing the results beyond its initial application. Examples of such operation could be read-only operation. You can read multiple times, and it will not change the state of the system. Adding to a set is idempotent too. The same items can be added multiple times to a set with the same result. Same with determining the maximum value out of vector of some, out of set of some values. Not much, yeah? Still, it can be used to build, for example, Apache Cassandra distributed database. It employs add to a set to manage data in column families and determines max of 2 times stumps for conflict resolution. So it is the idempotent system with very good distributed ready properties. But this could be not generally applicable for all business systems to build them only from idempotent operations. So we could employ another trick. A system could be idempotent if it has its operations ordered, and we throw away a request for transaction if we know this transaction was already applied to ACID storage. So always retry policy can be applied only for idempotent operations. Let's try to implement make new friendship as an idempotent operation in ACID data store. Here we have a client, it sends a make new friendship request to a server. A server checks, was it applied before? Are we friends already? If it was not, so it changes the ACID store and fails. Client waits for a timeout, server does not respond, and retries this request to another replica. Another replica checks, was friendship already established? So this operation was applied before, so it does nothing and just returns a success response. Please note that there are no any kind of "you are already friends" exception which thrown out of the replicas operation. It responded like it did this operation. Well, adding friends to a set could be easily checked for a duplication, but actually any operation could be checked for a duplication using sequencing. Then, before sending a request to make new friendship, client generates a sequence ID of operation and sends operation with this ID to a server. So server checks in this operation ID in list of processed IDs and makes processing only if it does not include it in this list. What could be used as a sequence of ID number? It could be just monotonically incrementing number, for example. It has obvious drawbacks. If there are several clients communicating simultaneously, it is difficult to maintain monotonically increasing number across a cluster of machines. So still, this is used in, for example, TCP/IP protocol. It could be current time. Time in milliseconds is naturally monotonically increasing. So we can use it, but still it is difficult to maintain its uniqueness having several clients. Still, we use this kind of sequence in our messaging system. We use a concatenation of chat ID, author ID, author of the message ID, and the current time, and this is compound message ID. So this is not pure and fair current time millis, but still. Another drawback is that there could be only 1,000 operations per second for this exact type of this operation ID, because there are only 1,000 milliseconds in 1 second, obviously. So for loaded operations, we could use a time-based UUID. There are no built-in implementation of time-based UIDs in Java language, so we use third-party library here. Here it's URL, you can check it out. Still, for idempotent operations, we would not apply always retry policy everywhere. Let's take a look at the second step of make friendship to see why. We need to refresh cache cluster with new data here. How this is implemented? So we have our weighted quadrant cluster, so we refresh the data of the new friend. A client must call all replicas of a distinct partition. But nobody can guarantee that no replicas will fail during this process. They could just not be running at the moment. Always retry policy in this case is meaningless because we don't know when the failed replica will be operational again. So retry is meaningless, but without it, data or the failed replica will diverge from the rest of the cluster. And this divergence will be more and more as time passes. So what we're gonna do? We synchronized our data from the database table. This is simple. In each of the cache instances, there are a background process reading modified records from a table and applying changed data to memory in a forever loop. The same process is performed at cache instance startup, reading all changes made from a database since the time moment this instance was last known as operational up to a current moment. Having this implemented, we are trying only once to refresh data in each replica, failing and leaving it for background synchronization process. What can go wrong else? Let's do it again. Client sends a make new friendship request to application server, but server started to GC a lot to garbage collect a lot. As a result, server is becoming slower and slower. So client waits for a timeout as expected, but at this time, this web frontend has other clients sending a lot of the same kind of the same queries to it. And to process them, it must send requests to the same just gone slowpoke server. And they also stall waiting for a timeout. Very fast, this web frontend dies as well. This death could be because of the thread pool exhausted, or because number of connections come to its limit, or the end of its memory. Whatever reason. What we're gonna do? We cut off server from client. So client stops to send requests to a server if it failed X of this client requests for the last second. This number is configurable. We use 80 as a starting number. Clients don't send requests to the failed server anymore, but they send their requests to that server replicas instead. And that start a background thread which periodically checks for failed server availability. If server starts to reply normally, then after a minute or two, client starts to send its requests to the server again. So server processes client requests normally again. This is simple, robust, and reliable, and this worked well for some time. But as the load and server number increased, we started to face another more interesting effects. Let's imagine we have 10,000 clients sending requests to a front-end server, and this front-end server sends necessary requests to a back-end server. This back-end server is good and powerful and has 24 CPU cores, so it is capable of processing each operation on 1.5 milliseconds in average. So its capacity is to serve up to 24,000 operations per second, a good 2 times reserve. All is working good, and then this powerful backend server becomes slower, only for a bit. It starts to swapping some pages. Java heap slowly reaches its limits, so the old GenGC fires a bit too often. So what happens further? The operation processing becomes a bit slower, so average operation processing time raises to 24 milliseconds. We are still within the 1.5 second timeout. All looks good, but the capacity of this server drops to only 1,000 operations instead of required 10. So it can't keep up with the rate of the request from client, and sooner or later client is dead again. This happens even before it can figure out that server is failing, because there are no timeouts. All operations are processing, only a slightly bit slower. So, what to do? We can set timeout to 2.4 millis, right? Yeah. But this is not applicable because there naturally could be operations that are processed more than this time. This is only an average. So there could be some operations taking longer. Another option is to cut off the server. If its average processing time becomes more than 2.4 millis. So we can cut it off. It's slowing down. This later case we actually tried to implement in production, but quickly figured out that this option is hard to maintain. Moreover, it's not reliable. if, for example, to set this limit manually, and one of operators start to experiment with servers off-peak time, average comes to its limit, and voila, whole cluster are cut off from all clients. No servers, sorry. Automatic estimation of the capacity and average time is also very hard to implement on distributed system, and this is not reliable. So we don't use this kind anymore. What we are employing now is the speculative retry policy. So we have some kind of idempotent operation, and instead of waiting on a single app server replica to respond and timeout, we send the request retry to another replica simultaneously with the original request. And clients consider operation done as soon as it receives a response from the fastest replica. So we make requests to replicas before timeout. And it turned out to be very good. It dramatically reduced 99th percentile of operation latency. This turned out because latency is not suffering now from individual server slowdowns. We work as fast as fastest server response. It is even good noticeable on average latency as well. Of course, this also makes the whole system more stable, because operational latency becomes more stable. Latency jitter is also eliminated. Of course, this policy is not applicable everywhere. You must have idempotent operations. And it generates additional load to the system. Additional traffic is also to consider. But these could be balanced. We could make speculative retry not always at once, but only when waiting for operation to complete is close to 99th percentile of the latency, or more than average of the latency. So number of such speculative retries becomes less. But we don't use these advanced techniques. We use dump, simple and reliable. We just send request to 2 or more replicas and wait for the fastest reply. Yep, exactly. We send 2 requests at once in the same moment. So I told you about making failures of individual replicas, but did we consider all possible failure scenarios? What else could possibly fail? All replicas of a service could be fail at once. So we can't ask replica. It's gone to. Whatever number do you have, 1, 500 replicas, they all can be down. Because of the excessive load is the first reason of it. Too many queries is being sent on cluster, all replicas become overload. Cluster is dead. Excessive paranoia also could be a reason. Any kind of automatic bots cutting off network access from legitimate servers, thinking these are some kind of hackers, for example. Other adverse reasons, including massive outages of network and electricity, and what else can happen? All this simultaneously, unintended, in any unintended and unthinkable combinations, in the worst possible sequence, of course. So what to do if all replicas does not work? Our intent here is so our system stays resilient, so we can do this. We can degrade. This means to degrade some of the functions of the system we can't run, so whole systems stay operable. We could degrade inconsistency. For example, we have user caches and ACID storage with users. As a part of user login operations, we write fact that when did last time the user logged in and from which location. So we try to write the time to a storage and discover there is no storage available, no single replica. So we do allow user to log in and use the site. Yes, we lost some data, but users still can work with the crew. We can use incomplete data. Do you remember split and merge? So we split requests to several servers and lost replies from some of them. So strictly speaking, this data is incomplete, inconsistent. When we still just show this partial data to user, but we could restrict some actions user can do with this data. Or we can tune feature off completely. You can see an example of this here. We turned off the games feature, but the rest of functionality, photos and groups, are working normally. Let's take a look how this tricks with partial data rendering could be implemented in code. So this is our good old user cache remote interface. Instead of just returning a collection of users, we return this. It is wrapped by this interesting object. Together with the data itself, it carries out an inconsistency flag, which we set when not all partitions responded. And to finalize this, we have another interesting stuff. This is called remote stop. This remote stop is client-side code, and it gains control when and only when whole cluster is unavailable. And all it does, it just returns an empty collection with inconsistency flag set. For operations requiring consistency, stop code throws out some kind of unavailability exception, or depending on the nature of the data, if operation could be just lost in this case, then this code just would be no operation. All this is nice in theory, but how could be sure that our system works as designed in case of failures? Is it resilient? And to be sure we got it programmed right, we must test it, of course. But what to test? Of course, we should test the product we do. But there is some problem. We do releases of our product every single week. So we must every week test for character actions on dozens of failures and their combinations. Standard solutions. Should we test standard solutions to know how it behaves on a failure? Microsoft SQL, Cassandra, good distributed database. Should we test how they fail? We absolutely must. Testing standard solutions is a challenge to find all hidden bugs or behavioral features of these systems, because you didn't develop these systems and cannot figure out what can go wrong in the failure and why. Operations on production environment also has to be tested, of course, if they are not automated. So to test our own product, we developed a system and named it Gorilla. This is being run as a part of pre-production testing every week. So what it does, it runs on our staging server and detects which network connections are established from front-end to a particular back-end server. This is necessary because these connections could change as code evolves. Then it drops these connections using IP tables. This way we simulate failure of backend replica or all replicas failure and runs auto testing. This is repeated for each distinct type of backend services. So what we check? Front-end server must work. Nice messages should be rendered to the client where they should be rendered. Only feature which are affected by a failed backend server really doesn't work, and other features must work. And we also check that front-end server can start with all replicas of backend server unreachable. It is commonly seen in initialization code to open connection to a database, wait for a connection to be established, and then continue initialization. But what happens if your database is dead? You can start up your backend server, even if this database is some kind of not important at all. So these tests allow us to test something before it hits the production. But this does not necessarily mean that something really works right. To be sure, we use production diagnostics and monitoring systems a lot. So what we use it for? To know that something does not work. When we have so much servers and distinct kind of microservices, knowing them not working could be annotated. If they are not working, this could be annotated for a long time. To track down to the source of the failure fast, and to try to prevent same kind of failures in future. So we use Zabbix for hardware monitoring and Cacti for pure technical charts like CPU, memory, and so on. But what is most important to us, we collect a lot of operational metrics. Every call made through any remote interface is counted and written down to our statistics storage. We write name of operation, counts of successful and failed calls, and its latency. All these is collected, aggregated, and sent to the statistics storage, where they aggregated and various kind of charts can be shown from it. We can see operational statistics and trends, aggregated number of successes and failures on all servers, and latencies for each operation, average, max latency, percentiles. And some dynamic filters could be applied on this, so we can drill down to each individual server or whatever else. All this looks something like this and this and this, and we created a lot of dashboards from this long and big and have a dedicated monitoring team. They look through all these ton of dashboards and look for anomalies. Is there any kind of failure? So part of the monitoring team get blind. Another part gets smart and created an automatic anomaly detection system. Here we can see a real screenshot of this system showing a detected anomaly. Web front-end latency is worsened. And traverses this source down to a video service. And it shows this traverse in form of this nice graph. This system traverses through all of the thousands of charts every 5 minutes and makes sure these anomalies are detected. This kind of analysis humans can't make. So this is all I wanted to tell you today. Here's a short summary of all my words. The possibilities of failures are endless in distributed systems. You will always experience something new, unexpected, and unforeseeable. We could not fully prevent failures. We could only mask them through redundancy of information, time, or hardware. If failure can be masked, we should degrade, but not stop our operations completely. We should test our and standard systems failures like we test normal features. An essential part of a distributing system is production diagnostics and metric system, which aids in failure testing, detection, and prevention. Thank you. Questions? We have a time for questions, I believe. If you are looking for more, I provided here some of the links. You can surf the internet. The last one is really good. This is the course of the Yale University on Distributed Systems Theory. Anyone? Questions? There are agents of Zabbix running on each of the hosts, and that agents send their parameters through SMTP, I believe. SNMP, sorry.
The system is overloaded, and Zabbix performance, how you measure it? Because a lot of, as you said, that you everything log it to Zabbix and sending by agents, and because a lot of requests, too many for Zabbix, I think.
I fear I can't answer your question. You have to meet someone who did the I have the one of our operations engineer here. He may be
Maybe
in more.
working like analyzing your logs and it's a background process.
No, we don't analyze logs.
Okay.
This is absolutely not working at our scale. The main idea is to make these logs even not written at all, so the data is not even extracted from logs. We generate the data to as early as possible, the original data, and send it in binary format to whatever we want. So something like that. If you want some, I really don't saw Zabbix from this perspective. This is more about operations. Sorry, I can make only speculations here. Alexei, you please stand up. So this is Alexei, one of our operations engineer. If you have questions about operations, you can safely ask him about all the technical details. Thank you. Yep.
So my question is about storage. For example, if you have several instances of the same microservice, what about storage? Do you share the same storage for all instances, or each instance gets its own storage?
Moreover, each microservice gets its own machine. So we run only one microservice instance per machine. So the storage is typically local to the machine. There are no shared storages configuration.
But you have, let's say, several instances of the same microservice.
If we have several instances for the same microservice, then we place them on the different machines. And these machines are located preferably in different racks and different data centers.
So we have some kind of mechanism to synchronize data between those.
Yep, exactly. This is why we use distributed data storages like Cassandra and Voldemort and a lot of in-house developed storages like this.
Thanks.
I believe that there's time. Our time is out. I'm personally be here for the rest of the day. You can find me safely at our booth at OK.ru. Please welcome, come, don't hesitate to ask me some weird questions. I'll try to answer them. Thank you for your time.